Sample problem number 10. So for sample problem number 10, we have an enclosure. The vertical height of the enclosure is 0.8 meter. Thus, this is a 2 meter wide double pane window consists of 2 glass sheets separated by 2 centimeter gap at atmospheric pressure. If the glass surface temperature across the air gap are to be 12 degrees Celsius and 2 degrees Celsius, determine the rate of heat transfer through the window. So the temperature of each surfaces of the glass is given. The width or the distance between the gap is 2 cm and then the height is 0.8 meter. So between the gap, it's filled with air. So our assumptions for these problems are: steady operating conditions, air is an ideal gas, and we do not consider radiation heat transfer. So the properties of air at the average air temperature. So for enclosures, we evaluate at the average temperatures between the two surfaces. So that's why we have 7 degrees Celsius. And looking at our table and then interpolating at 7 degrees Celsius, since we do not have the value for 7 degrees Celsius, we interpolate and then we obtain the value of our thermal conductivity, Prandtl number, our kinematic viscosity, and our coefficient of volumetric expansion from the film from this average temperature. So the rate of heat transfer can be calculated using our formula, and we just simplify it directly since we know that our H is just equals to K over L times the Nusselt number. So we just, instead of putting H, we just directly substitute the value of H, which is K and U over L. So looking at this equation, working equation for the heat transfer which is required, we need to solve for the Nusselt number and the surface area. So for the surface area, it is just equals to the height, and it is given actually. So 0.8 meter high and 2 meter wide double pane window. So the surface of the window is 0.8 meter by 2 meter. Take note that this 2 cm is the gap. So the surface of the window is 0.8 meter by 2 meter. So this is the view of the window. So the area of the window is 1.6 meter squared. So from the aspect ratio, so which is the height divided by the gap, so that's 0.8 divided by 0.02 meter, our aspect ratio is 40. For this particular aspect ratio, we will determine which Nusselt number is applicable. So we will look at our table. So from the table, when the aspect ratio is between these values or equal to that value, we can use this. So for the aspect ratios between 1 to 2, 2 to 10, and 10 to 40. So for 10 to 40, we will use this Nusselt number. We will use this equation. So the characteristics length for this equation is equals to the distance between the two glasses. So 0.02 meter. So we already have H over L, and the Prandtl number is already available. So we need to solve for the Rayleigh. So for the Rayleigh number, substituting the values that we have in our equations for the Rayleigh number, we can solve for the Rayleigh number with a characteristics length of 0.02 meter as 1.051 times 10 to the power of 4. Then substituting to our available equations for the Nusselt number, so we have a Nusselt number of 1.401. And finally, substitute the Nusselt number to our rate of heat transfer equations as well as the surface area that we solved earlier. So that's why our convection heat transfer rate through the window is 27.08 meter between these two enclosures. Number 11. So for sample problem number 11, we are given with two concentric spheres of diameters 20 cm and 30 cm. The surface temperature of the two spheres are enclosing air at 320 Kelvin and 280 Kelvin, as you can see in the diagram. We are to determine the heat transfer rate from the inner surface of the sphere to the outer sphere by natural convection. So these are our assumptions. So for the properties, we evaluate it at the average temperature between the inner and the outer spheres. So that's why we have 27 degrees Celsius. And interpolating A15 at 27 degrees Celsius, we will solve for the thermal conductivity PR, the dynamic viscosity, and the volumetric coefficient of expansion. Spheres, the rate of heat transfer between the spheres can be calculated using the equation found in slide number 95. So for spheres, so the rate of heat transfer is K effective pi di times dO over LC times the difference of the temperatures. Take note that our characteristics length this time is this one, and then for the value of the K effective, we will use this. So we need to solve for the F sphere using this equation. Use this particular equation in evaluating the rate of heat transfer between the spheres. So as you can see, we already have the value of DIDO as well as the temperatures. So we will calculate for K effective and the LC. For K effective, using the equation, using this equation, so we need to solve for the unknowns. So PR is already given. So we will solve for F sphere as well as the Rayleigh number. So for the F sphere, this is our equation for the F sphere. So at a characteristics length, which is the gap or the distance between the two concentric spheres, which is 5 cm, and then substituting the values for diameters, inner and outer diameters, we can solve for the F sphere. And then for the Rayleigh number, using the same characteristics length, we can also solve for the Rayleigh number. And then we substitute these values to our effective thermal conductivity for this particular sphere. That's why we have 0.11045. And then finally, we can solve for the convection heat transfer rate between the sphere, substituting all the values to our original equations for the heat transfer rate. So 16.66 watts.